Assalamu alaikum everyone. Welcome to the lecture number 13 of digital signal processing. Students, we have covered basics of signal and system that was considered to be the first part of our syllabus. Now we are proceeding towards the part B, which is the frequency analysis of signal. In this lecture, we are going to cover the basic introduction of frequency analysis of signal. How it is beneficial for us to do signal analysis based on its spectrum or frequency knowledge. We will see the analysis techniques of signals and the tools utilized for this analysis. As you all know, there are various mathematical tools available to determine the frequency contents present in the signal. But we will restrict our discussion towards the most powerful tool of signal analysis, which is Fourier series. Contrary to the analysis of signal, there is synthesis of signal also, which shall be also discussed in these lectures. Regarding lecture number 13, we are going to discuss in this lecture CTFS, which is continuous time Fourier series, CTFT, which is continuous time Fourier transform, DTFS, which is a discrete time Fourier series, and DTFT, which is discrete time Fourier transform. We will discuss each of these techniques in detail in the later slides. A question arises in our mind that why it is necessary to do signal analysis and what is basically meant by analysis of signal. So in simpler words, analysis means to decompose or disintegrate any physical phenomena into its smaller components or modules in order to understand that phenomena. So as we are more interested in signal analysis, so we are going to disintegrate or decompose the signal to analyze or understand the phenomena or analyze the information or content that is present in that signal. So the basic purpose of analysis is to observe, or we can say to examine or to investigate. You can see from the example, we have taken a glass prism and passed white light into it. After passing through this glass prism, this white light is split up into its constituent colors. You can see violet, blue, green, yellow, orange and red, which is basically the spectrum of this white light. So basically, glass prism is served as a tool to analyze this white light, which break up the white light into its ingredient elements. Similarly, in signal analysis, some mathematical tool or technique is required to disintegrate any complicated signal into its constituent or ingredient elements. So from this example, you can understand that any complicated signal can be disintegrated into its ingredient elements with the help of some mathematical tool. So we can say that signal analysis is basically splitting up or decomposition of a complicated non-sinusoidal signal into number of simplest components, and these components are sinusoidal in nature if we talk about the Fourier series, which is our topic of interest. And why we are doing this signal analysis? Because our main purpose is to explore the nature of basic building blocks. However, there are several other techniques available also which can analyze any complicated signal, such as you may heard of Laplace tool. Laplace also Laplace can also be utilized to analyze any signal. But the difference between Laplace tool and Fourier tool is that Fourier actually disintegrate any complicated signal into the simplest form, which is sinusoidal waveforms or sine waves or cosine waves, or in general sinusoids. So Fourier basically breaks up the signal into sinusoids, whereas Laplace tool can be utilized to break the signal in exponential form. But we are restricted to Fourier because of several reasons. Fourier basically, as compared to Laplace, is more preferable for analysis of signal. But for system analysis, we usually prefer Laplace transform, because Laplace transform also tell us about the stability of the system, which Fourier does not. However, Fourier is very strong mathematical tool which is easy to interpret graphically. In this slide, you can basically observe that we have used two prisms. One is basically splitting up the light into its constituent elements, and the second one is used to combine all these elements to again produce the white light. So the first prism, this one can be actually analyzing this white light, and the second prism is basically synthesizing all the ingredient elements to again form the original signal. So basically there are two terminologies associated with signal analysis. One is signal analysis, which is to break down the signal to observe what's going on in the signal or what is the frequency component present in that signal, and to combine or add all the ingredient elements or all the frequency components to again formulate the original signal is basically synthesizing of signal. So in the later slides we are dealing with two equations. One is used for signal analysis and the second one is used for signal synthesis. So I hope the difference is clear between these two terminologies. First one is signal analysis, which is used to observe the basic ingredient elements, And if we want to combine all the ingredient elements to again formulate the original signal, then we use the synthesis equation. Analysis is also known as, generally frequency analysis is also termed as spectral analysis, because by this process we are actually going to observe the spectrum or the frequency components present in that signal. That's why this process of frequency analysis is also known as spectral analysis. However, there is a difference between spectral analysis and spectral estimation. The difference is very simple. Spectral analysis is one if we are going to analyze the signal by using some mathematical tool, then we will say this as spectral analysis. But if we are analyzing any real world signal based upon real values or real measurements, then this is known as spectral estimation. So a real-time signal with real-time measurement, we will get spectral estimation, and if we are dealing with the mathematical tool based on paper pencil approach or using some lines of codes to process the information, then we will say spectral analysis. So here in this slide you can see various techniques available to analyze any real world signal. These techniques are based upon Fourier tool. As we conclude in the previous slide that we restrict our discussion to the Fourier tool. So all these techniques are pertaining to Fourier tool. However, these techniques are different because each of these techniques will be applied in a particular scenario. In this slide, I am going to brief you when we apply this technique. It is very simple, and the technique name also implies its application. If you see, the first technique written on the slide is continuous time Fourier series. It is abbreviated as CTFS. So basically there are two parts. First one is continuous time and the second one is Fourier series. Recall that you have classified the signal on various parameters in the initial lectures. One parameter is the continuity in time axis, or it may be a discrete time signal. So if you are going to analyze a signal which is continuous in time, so you will apply this technique, because it is clearly mentioned that this technique is going to apply at continuous time signals. But again, second condition or second part is Fourier series. So Fourier series is actually telling us that this technique is actually going to be applied on only periodic signals. So in actual, this technique, which is continuous time Fourier series, is applied only on those signals which are continuous in time and periodic in nature. So we have to, if we have any real world signal or we have to analyze any signal, then we must see its two parameters. First one is continuity in time and the second one is periodic in nature. So if the signal satisfy these two parameters, that it is in continuous in time and periodic in nature, then only we can apply this technique, which is continuous time Fourier series. Similarly, second technique, which is continuous time Fourier transform, as its name implies, it only applies to continuous time signal. But the second part is reflecting, which is Fourier transform. It is basically telling us that this technique can only be applied to those signals which are aperiodic in nature. So, series applied to the periodic signals and transform is applied to the aperiodic signals. So, if you have any signal which is continuous in time and aperiodic in nature, so you may apply this technique, which is continuous time Fourier transform. Similar discussion for the third technique, which is discrete time Fourier series. I hope you understand this concept now, that which technique is going to apply on which type of signal. So the third technique is basically discrete time Fourier series, and as its name implies, it will only be applied to those signals which are discrete in nature and periodic. So if you have any signal which is discrete in nature and also it is periodic, so you have to apply this technique, which is a discrete time Fourier series. Similarly, moving on to the fourth technique, which is a discrete time Fourier transform. Again, Fourier transform is showing that this technique can only be applied to aperiodic signal, and discrete time is showing that this technique is applied only to those signal which must be aperiodic as well as discrete in nature. So we have to look at these two parameters simultaneously. If the signal is discrete in time and aperiodic as well, then only we can apply this fourth technique, which is DTFT. So these basically are the four major classification or main techniques, which are CTFS, CTFT, DTFS and DTFT. But all these techniques cannot be applied practically. However, we can apply them on paper pencil, but they cannot be applied on a real-time signal or a practical signal. So, because of their limitation, we will discuss the limitation in later lectures, but for your understanding, these techniques are basically the mathematical equation. We put the equation of signal in that equation. It may be analysis equation or synthesis equation. We actually put the signal model in that equation and we will get the result. But practically it is not possible to compute some of these techniques because of some very implicit restrictions or limitations. So we have another technique, which is discrete Fourier transform, which can be, as its name implies, it is Fourier transform. So you may think that this technique can only be applied to the aperiodic signal, but this is not the case. Discrete Fourier transform can be applied to periodic as well as aperiodic signal. So do not mix that concept which we have developed in the first four technique, that series is applied to the continuous signal, series is applied to the periodic signal and transform is applied to the aperiodic signal. This is not the case for discrete Fourier transform. It is not valid for DFT. For DFT, we can have a signal which is periodic as well as we can process aperiodic signal, or we can analyze any aperiodic signal with the help of DFT, which is discrete Fourier transform. However, signal must be discrete in nature to apply this technique. So I hope that this point is clear to you, that discrete Fourier transform is applied to any signal which is discrete in nature, and it may be periodic or it may be aperiodic. It can be applied to both of these signals. Moving on to the next technique, which is fast Fourier transform. Again, fast Fourier transform is basically the advanced version of discrete Fourier transform, in a sense that its speed is much greater as compared to DFT. So it is basically the faster version of DFT. Same algorithm is used, but some steps which are redundant, that steps are excluded in fast Fourier transform to save the computation time. So by the same speed processor have, for example, we have taken a processor of some specific speed, and we are going to perform the analysis of our signal by using discrete Fourier transform and by fast Fourier transform. So fast Fourier transform will give us the final output or final result in much lesser time as compared to the DFT technique. So both the last two techniques are similar. The only difference is in the computation time. Fast Fourier technique is much faster as compared to discrete Fourier transform. However, there are various algorithms developed for fast Fourier transform, such as radix 2 algorithm, radix 4 algorithm. We will discuss these algorithms when we are discussing the technique which is fast Fourier transform. But for the time being, I hope that a picture is clear to you, that if we have this nature of signal, then we have to apply this technique, and due to some practical limitation, we cannot apply all these technique practically. However, we can solve this technique using paper pencil, but practically it is not possible. For example, first technique, which is continuous time Fourier series, you cannot develop an analog circuitry to perform continuous time Fourier series. You can solve it on paper pencil. We will solve a signal in the later slide with the help of CTFS. But if there is some real world signal and we are going to process it with the help of CTFS, then we are unable to develop its circuitry or develop its basically analog components to perform this task, which is CTFS. So we will see it in the later slides, that what are the limitations of all these techniques, and why we are opting fast Fourier transform as the most reliable technique to do signal analysis. As we have discussed that we are more interested in Fourier tool, and Fourier tool basically depends upon sinusoidal signals for its representation. As the Fourier series statement is, any periodic signal can be disintegrate or can be basically divided into smaller components, and these smaller components are basically sinusoids in nature. So this is the expression or statement of Fourier series. So as the Fourier series rely on sinusoidal signal, so we are going to understand the sinusoidal signals in much detail in these slides. First, we are going to represent our physical phenomena, and here the phenomena is chosen as uniform circular motion, and that motion is described by a sinusoidal signal, and it is mathematically represented by using the sine expression. So basically in this slide what is going to happen, that we have a uniform circular motion phenomena, and we have taken a particle, and this particle is basically rotating on the edge or border of a unit circle. So its radius remains the same, and its radius is assumed to be a in general. So basically the phenomena is this is the particle, and this particle is moving in the counterclockwise direction, and we take counterclockwise as positive, and omega is the angular rotation or angular velocity of this particle, and as it is uniform circular motion, so it is moving with the uniform speed, and a is basically the radius, theta is the angle it is formed with the x-axis, and there is a time to travel certain distance. So this is basically a phenomenon, and actually we are going to represent this phenomenon with the help of sinusoidal waveform. How? If you are going to observe this particle along the x-axis, you can see that I is drawn here, so it means that you are seeing this particle moving in a unit circle along this direction. So you are here along the x-axis and particle is moving, so you will basically see this type of sinusoidal waveform if you plot whatever you are seeing with respect to time, because at the time is proceeding, particle is moving from its initial position to its extreme position. You can see that initially the particle is here, and at this time is equal to 0. You plot this point, and as the particle starts revolving, after some time it is at this position, which is its maximum position. So this plot is basically time is exceeding or time is passing and your particle is moving, and at this time your particle is at extreme position. From this extreme position, particle again descend or move down, then you will obtain this type of curve. When it again goes to this side, then you will get another waveform like this. You may assume that this waveform can be pasted here. So in this way, the phenomena of this uniform circular motion observed by your eye can be represented by a sinusoidal signal, because it is forming a sine wave. You can think of multiple particles also, and for those multiple particles you can assume different amplitudes as well as different frequencies. So what you will get? You will get multiple sinusoids. It is the one sine wave, you will get multiple sine waves, and that sine wave, because you have considered different amplitude and different frequency for each particle, then you will get multiple sine wave, each of which having different amplitude and different velocity. So in the end you will get multiple sine waves, and you will add up all those to get one uniform or one complicated signal, and that signal is basically your phenomena, is representing actually your phenomena. So you may imagine that this phenomena can be split up into its building block or its sinusoidal components, each of which having different amplitude and different frequency. Moving on to the next slide. In this slide, basically Euler's identity is represented in form of frequency domain. Basically we have two domains. First one is the time domain, which is most common, and we usually get all the signal in time domain. And to analyze the signal, we actually convert these signals into frequency domain. By converting in frequency domain, basically I mean to say that I want to analyze the frequency components present in that signal. So if I am getting the knowledge of frequency components present in that signal with the help of some graph, then it is basically a frequency domain graph or frequency spectrum. So please recall the Euler's identity. Euler's identity basically relate the exponential signals or exponential form to the sinusoidal form. So you can see in this slide also cos 2 pi f naught t is written with the help of Euler's identity, and it is divided into basically two parts, which each of which composed of exponential impulse signal or exponential curve. So actually we are transforming this time domain signal into the frequency domain. In the part A you can see you have cos signal, and in the part B you can see you have a sine wave. So, and the difference is basically the phase difference. You can see that sine wave is starting from the zero value and cos wave is starting from the maximum value. So these are basically, and generally we call sine and cosine as sinusoids, and these sinusoids can be represented with the help of Euler's identity. For cosine wave, Euler's identity is e raised to power j 2 pi f naught t divided by 2 plus e raised to power minus j 2 pi f naught t divided by 2. It means that this cos signal can be represented in the frequency domain, or in other word we can say it is composed of two spectral lines, each of which having the magnitude half and frequency f naught, which is the actual frequency present in that signal. You can see here that this cos wave is actually having some frequency, and that frequency is represented by transforming this cosine waveform with the help of Euler's identity at exactly that frequency, which is f naught, which is the frequency of this cosine wave. We are getting the impulse, or we can say spectral line or simple indication at that particular frequency which is present in the original signal. So this is very interesting thing, that with the help of Euler's identity we are actually representing our time domain signal into frequency domain. In this signal you cannot predict what the frequency of signal is, but by looking at this graph you can easily say that for this signal frequency is f naught. F naught may be 1 Hz, 2 Hz, whatever the frequency is. But by looking at this graph you can easily comment that this is the frequency of our actual cosine wave. But you can also notice that the magnitude is divided by half. Here it is 1 over 2. So the magnitude or strength of this spectral line is actually divided into half. But it is not much more concern to us, as we are getting the actual frequency by using this frequency domain spectral lines. Another interesting thing you may observe from this plot is that we are actually getting the double-sided spectrum. Exactly what frequency we are getting at positive x-axis, the same frequency which is negative of f0 is actually we are getting at negative x-axis. So the interesting thing is that we can actually discard the negative side information and only consider the positive side information as far as we are interested to know about the frequency components or which frequency is present in that signal, because the same information is we are getting on the positive x-axis, which is we are getting on the negative x-axis. So both the spectral lines are on the same frequency. Here we have assumed a cosine wave of single frequency, which is particularly f0. So we are getting two spectral lines, one at f0 and on the negative side it as minus f0. So if we discard the negative side information, we are getting enough information from the positive side also. So this means we can save our memory and the computation also, and we are getting the actual result from this also. So basically how the lines are represented: exponential exponential raised to power j 2 pi f naught t. At f naught we actually put a spectral line of magnitude half, and at minus f naught we actually put a spectral line of again magnitude minus half. In this way we are getting this frequency domain plot. But for the sine wave, there is something very interesting and different. This spectral line is basically actually rotating, or we can say that these phasors are actually rotating. How? It is very simple. You can see that the expression or identity for sine wave is sine 2 pi f naught t is equal to e raised to power j 2 pi f naught t divided by 2j and plus this. Okay, are you getting my point? That these two terms are actually having j in the denominator, and when we are shifting this j into the numerator, the sign become opposite. So the first term become negative and the second term become positive. And as far as plotting is concerned, J is nothing but a 90-degree phase shift, which is represented in the phasor diagram or the spectral line. You can see that in the cosine plot we have a spectral line at f0, but for the sine plot we have f0, magnitude is half, okay fine, but magnitude is minus half. Or minus j, because half is applied to the magnitude and minus j is left. So j is basically the 90-degree phase shift. If it is positive j, then it shift the line to counterclockwise direction, which is assumed to be positive, and if it is minus j, then it shifts our spectral line towards the clockwise direction. So you can observe that this spectral line basically transferred to the imaginary axis or along the imaginary axis, you can see here, because of this minus j sign, and this is positive j, so this spectral line is shifted towards the 90-degree in counterclockwise direction. So we are getting this frequency domain plot. So students, I hope that sufficient interest have been developed from your side after listening to this analysis techniques and this very interesting diagrams, and we will inshallah resume our lecture, this discussion, in the next lecture. Thank you.